Bip. Okay, so where we are right now then is we are playing around. Well, I'm going to center myself on the screen because I notice I'm not really centered on the screen too good either, am I? Whatever. I'm not that great to look at anyways. It doesn't matter. But what we began to do at the end of the time Monday was we began to look at the magnetic phenomenon and how matter is magnetized. So what I briefly discussed at the end of the period on Monday, like I like to do, we'll do just a brief recap of what we had said. What we had said was that the magnetic phenomenon is really just a hidden form of the electric phenomena. They are very closely related. Now, in actuality, this was not understood for a long time, not until the 1800s. The relationship between electrical attraction and magnetic attraction was not known until the mid-1800s. And what magnetic phenomena end up being are an effect that is generated when charge moves. When charge is sitting still, the interaction is what we call electrostatic, and that's why they often use this word electrostatic. When charge is not moving, it can still attract itself. It can attract itself by positives pulling on negatives and negatives pulling on positives, or negatives and negatives pushing apart, and positives pushing apart. Now, when charge moves, they still have the ability to attract plus and minus, or repel minus minus, or plus plus. But when charge moves, suddenly and magically, a completely new phenomenon develops. And this completely new phenomenon is the magnetic phenomenon. Now, probably for everyday experience, we have more applications and uses of the magnetic phenomenon of attraction than the electrical phenomenon of attraction. Even though the magnetic phenomenon cannot occur without the electrical phenomenon itself. So then the idea with magnetism is in many ways, has similarities to the behavior of electricity, meaning we have two flavors of magnetism. And the two flavors of magnetism are not deemed plus and minus, because that would be confusing. They're deemed relative to the behavior of the magnetic field of the Earth. If you have a north magnetic pole, it will be attracted to the region of the Earth in the Arctic Circle. If you have a south magnetic pole, it will be attracted to the region at the bottom of the Earth in Antarctica. So what this is saying then is that we have these two types of attraction of relationships, but we also have the same idea of repulsion relationships, meaning if you try to put a north near a south, they grab onto each other. Just like if you try to put a plus near a minus, they grab onto each other. If you try to put a north near a north, they repel each other. And if you try to put a south near a south, they repel each other. Just like if you try to put a plus near a plus or a minus near a minus. Now, another thing that we mentioned at the end of the period last time was that unlike charge of an electrical sense, you cannot isolate the magnetic effect. When one exists in a material, the other one is also present in the material. Meaning, if you have a piece of matter which is magnetic, it automatically contains both a north and a south pole. So any material that you have is north and south. Now, what happens individually, though, what really makes a north and a south? Well, if a positive, the reason there are two poles to begin with is because there are two kinds of charge. If you move a positive charge, it's going to generate the north. And if you move a negative charge, it's going to generate the south. But in a collection of matter, we don't have individual positive charges. We don't have individual negative charges. We have all kinds of charges, and they're all moving. And when they move collectively, the same number are moving in one orientation to generate the north as that are moving in the other orientation to generate the south. So a piece of matter always contains both a north and a south pole. We cannot isolate a north pole piece, which we would call a north monopole, or a south pole piece, which we could call a south monopole. You can make a positive monopole of just positive charges. You can make a negative monopole of just negative electrical charge, but you can't make magnetic things singularly. They come together. And as I showed on a slide earlier, or I would probably, that might be where we're going to begin here today with my slides, that if you cut a magnet in half, you think you're going to cut the north loose from the south. Magically, the material in it recognizes that and regenerates the missing component. The one that you think is now only going to be a south pole will automatically generate a north pole to go along with that south pole. The one that you think is going to be a north pole will automatically generate a south pole to go along with that north pole. So we can't isolate these things alone. Okay, so what I guess I want to do then, that's just a brief recap of the phenomenon. We're going to examine a little closer now what makes a permanent magnet. We're going to examine the effects of the magnetic field, and we will see that they have many similarities again to the electric field, which we earlier had related to a gravity field. So there's lots of similarities between all these kinds of action at a distance creating a phenomenon in nature. Remember, when I say action at distance, magnetic fields can attract without touching an object. They can act through space to push or pull objects in that magnetic field. So we're going to examine some of those ideas. And of course, to do that, I want to do so on my slides. So I'm going to hit my Present Now button. And I'm going to present my screen as I always do. And then I'm going to flounder around here. And I'm going to share. I hope I'm hitting the right thing. Make sure I'm doing the right thing. Okay. So now I think I'm going to be sharing my screen. And then I have my thing here, and I'm going to go to my slideshow. Okay, and I do believe this is where we were. Let's try to see if we can simply describe this crazy magnetic phenomenon. Now, of course, as you can imagine, and I'm sure you can believe, to truly understand what's going on, we would have to have intimate knowledge of quantum mechanics. This high-level mathematics-based physics discipline that explains the behavior of matter at the nanoscopic level. We are not anywhere near any of that. So what we're going to try to do is what physicists commonly refer to as hand-waving arguments. We're just going to stand up here and try to build a mental picture of how the magnetic phenomenon exists and how it acts through matter. So again, as I said, and we mentioned this a little here a few moments ago, I can generate magnetism by charge in motion, and I can generate magnetism by moving either positive or negative charge. Now, then let's make some considerations of what would happen if I am able to move a positive or negative charge. First of all, if the charges are stationary, there is no magnet, period. Now, that doesn't mean there's not electrostatic attraction. That doesn't mean that the pluses don't pull the minuses and the pluses don't push the pluses. They still do. But once you start moving the charge, now you can have a magnet. Okay, so then I think it would be logical to assume, and it is correct to assume, that if you move the charges in the same direction, if you move a positive or a negative in the same direction, one will be making a north pole while the other is making a south pole as they move. So that's what you can assume, and I think that's a safe assumption. Now, the other thing you can maybe envision that might occur, let's just take a positive charge and let's move it in different directions. Does that cause a different behavior to the kind of magnet that it makes? And again, the answer is yes. So for instance, if I move a positive charge in some orientation from left to right, let's say when I move it in that direction, it makes a north magnetic pole. Now, if I take that same positive charge and instead of moving it left to right, I move it right to left. Well, when I move it right to left, it will now be generating a south magnetic pole. So the different charges moving in the same direction will make opposite poles. The same charge moving in opposite directions will make opposite poles as well. So there's all kinds of weirdnesses to what type and how these things will be generated. Now, of course, we're going to generally use matter in motion, charge in motion through matter. So then uniquely when there's charge in motion through matter, because of the polarization that's caused in the matter, then we're going to have motion of charge in both directions overtly or invariably. And so you're always going to end up in a solid piece of magnetic material. It's got to contain both the north and the south pole when it is made of any tractable, visible amount of matter. So one simple way to generate a magnet, and this is pretty much where we did end up last time, is in a current carrying wire. Current carrying wires, of course, have electrons hopping along through the material, through the conducting material. Remember, conductors facilitate the motion of charge. So I'm moving charge through the conductor, and then I am making a current. This charge in motion then naturally has magnetic characteristic associated with that. So this allows us to make what we call an electromagnet. An electromagnet generally is something that is a current carrying wire. It has to have what we would call direct current, and we'll be saying more about that later, but a direct current means all the electrons flow only in one direction. In an alternating current, the currents periodically switch, the electrons periodically switch, and half the time flow maybe clockwise through a circuit, while the other half of the time they flow counterclockwise through the circuit. Now, I don't want to get into the gore and detail of that differentiation right here. I would rather save that for the unit where we will discuss electricity, which is very shortly upcoming here, by the way. So we'll be describing that a little more in detail later. But I think your mom and them have heard the terminology that we employ to these kind of cases. When the current flows in only one direction, we call it DC, direct current. When the current hops between the directions periodically and equally, we call it alternating current, or AC. So we have AC current or DC current, depending on if the flow is in one direction or if it's in both directions. Now, AC is familiar to us when we plug into the wall. That is alternating current that we are always getting out of the wall and using for a wide variety of applications. DC is familiar to us as well, and as a matter of fact, most of the devices we operate would prefer DC, so most of the devices we plug into the wall have a way to convert AC into DC to operate the device. But a generator of DC that you should be familiar with is one that's shown right on this cartoon I'm showing here, and that's a battery. Batteries generate direct current. They don't generate alternating current. They make current in one direction and one direction only. Okay, again, I'm going to spend a little bit of time in our next unit talking about the relationship between currents and the different types of currents and the utility, and when we would like to have one compared to the other. We'll talk about that more in detail. For now, what is important for us in this particular unit is that if I have a direct current, if I have charge flowing in one direction and one direction only, I can use it to generate a steady magnetic object. Now, what you will see in my cartoon is I have a battery with a wire on it, and on the wire on the battery, it is wrapped around a nail. And if you don't know what nails are made of, they're made of iron. And if you're not familiar, iron and magnets go hand in hand. They are friends of each other. Materials that are magnetic, that are made out of substances that are permanently magnetic, are almost invariably iron. Now, I will say not all of them are, but the general ones that you encounter have some iron component to them. Now, what you'll see in my cartoon is that I have wrapped an iron nail with a current carrying wire, and that is what I'm calling an electromagnet. This is very commonly the way it is done. The iron itself is a highly polarizable material. Now, what do I mean by it being polarizable? We had talked about this before with regard to charge. And again, I hate to be repetitive, but I want to tell the story again very briefly so that maybe it'll tweak your memory and you'll remember about what I'm speaking. The polarization of charge occurs when you have electrically neutral objects that have, of course, made up of individual charges, but the charge is evenly distributed in them so that they are not net negative or positive. They are electrically neutral. But we can shift the balance on them by rubbing a piece of plastic against a carpet or against a fur, a piece of fur, a hide of an animal or something like that. And we can rub electrons off the carpet or the fur and transfer them to the rod. Now the carpet is positively charged compared to the rod, which is negatively charged. The amount of charge gained by the rod is exactly equal to the amount of charge lost, the amount of negative charge lost on the carpet. So now that I have this positive thing, what I will find is that if I put it near paper clips, suddenly the paper clips dance and they are attracted to the rod. It's not that the paper clips have suddenly been charged themselves. It is but that the paper clips have been polarized. The charge in the paper clips is evenly distributed. But when I put a negatively charged rod near the paper clip, since it is made of conducting material, the charge in it begins to move instantly and says, whoa, there's negative coming toward me. So the negatives run away. And the positives say, whoa, there's negatives coming toward me. I'm going to run towards it. So temporarily, the charges in the conducting material make a polarized distribution so that the end near the rod is more positive and the end far away from the rod, because the rod is negative, is more negative. The negatives don't like that negative rod, they run away. The positives like that rod and run towards. So now the paper clips have a natural attraction to the rod. That is polarization. So I explained that phenomenon, and now I'm going to turn to magnets. The same thing is true in magnetism, we learn. We learn that iron is polarizable not only by an electric field, but it's polarizable by a magnetic field. Now, this is not true of all metals, but it is certainly true of iron. Iron is highly polarizable by a magnetic field, which means this, that if you break the charges down in iron into individual magnets, normally they are evenly distributed, so that entirely a piece of iron is not magnetic. Okay, so what I mean is if you get an iron spoon out of a drawer, if you get an iron screwdriver out of a drawer, and you try to pick up paper clips with it, it won't do it because it's not a magnet. Or your refrigerator is not a magnet naturally. But if you put magnets near the iron in the refrigerator or in the screwdriver or in the paper clips, now the magnet, if you bring a north pole towards the iron, the magnets in the iron are polarizable. They can move. So if you bring a north pole near the chunk of iron that was magnetically neutral, now since you brought a north near it, south say, oh, I like that. And they start to migrate through the iron towards that north you brought. Norths in the iron say, oh, I don't like that. And they migrate naturally away from the north pole you brought near it. So there's a temporary polarization of the iron, and there's attraction between the magnets. And of course, this is, as I said, why magnets stick on the fridge. When I take the magnet off the fridge, all the little magnets internal to the iron just go normally in all orientations throughout evenly, and the fridge again is no longer magnetic. Okay, so the reason I'm speaking about this is you will note that I've wrapped a piece of iron with the current carrying wire. That induces the nail that is made out of iron that is wrapped with the wire to pick up the magnetic character of the wire. So I'm making the nail into the magnet that I'm going to use with the wire. What does this mean? If I wanted to pick up a car with just a wire, so I put the wire, I got a big current going through a wire, and it makes magnets. And I'm working in a junkyard, and I want to pick up the car with that wire and move it to another pile of cars. That ain't going to work because the wire isn't strong enough. It doesn't have the ability. If I tried to pick the car up with it, it will rip the wire apart. The wire just simply isn't strong enough to carry the car. But a big chunk of iron is. So I wrap the wire around the iron. It magnetizes temporarily the iron. As long as the current is flowing in the wire, the chunk of iron is a magnet. I put that on the car, and now that piece of iron is strong enough, certainly, to pick up the car. Now when I move the car over here, I turn the current off. And when I turn the current off, the little magnets in the iron say, oh, we don't want to be polarized. Now we want to go evenly distributed throughout. So they run around, and now the chunk of iron that previously was magnetic because I turned the current off is no longer magnetic. So the car falls. So an electromagnet is really nice because you can turn it on and turn it off by supplying a current, then switching the current off. Now there's also the phenomenon of naturally occurring magnetic materials. Now these were known by humans for 1,000 years now. We've known about magnets. You just get rocks that naturally come out of the earth, and they have what we would call permanent magnetic character. So this is not a polarized situation. This is the picture on the right is a polarized magnet that is generated only when the current flows. The situation on the left is a permanent magnet where the material is constantly having a magnetic field. Always, it's just always a magnet. Now the material traditionally, as you can see, the names are given below that material. These were called lodestones, or they were called magnetite. Those were the materials that were naturally permanently magnetic out of the ground. So we will try to give a little bit of insight as to what's going on in magnetite and lodestone that makes it permanently magnetic. Now, of course, this was very important and became applications for a wide variety of things that we use. I tried to mention a few applications of magnets that are important other than picking up cars and moving them around the junkyard. For instance, I mentioned last time, and I will say it again just in case some of us were tuned out at that particular point. This is how we make amplification of sound. When I speak into a microphone, literally there is a diaphragm in there that gets pushed by the air currents that I'm generating with my mouth. There's like a cone in there that feels the pressure of the sound and bounces with the sound coming in and out of my mouth. Well, that bouncing sound is now also the cardboard piece is attached to a little magnet. So the magnet moves around, up and down behind that piece of cardboard. And what that does is it translates that into current through a wire. So not only does current make a magnet, moving magnets can make current. So I translate that sound into an electrical signal that travels down the wire. Then through the wizardry of our electronics, it comes to the other end where it comes to another magnet. And the current is wrapped around that magnet on the speaker. And now the speaker carries the current to it from the microphone, and it starts dancing the magnet on the speaker, which pushes a big cone that makes the sound amplified and sent out, sending big sound waves, compressing the air around it. So that's one of the most obvious applications of magnets that is a benefit to our everyday life. But there are many others, and I would prefer maybe later when we talk about AC and DC circuitry, I'll give you probably the most important application of magnets. When we're making alternating current for our houses, we have to have magnets. We can't do it without magnets. Okay, so let's now turn to this picture on the left and try to explain something about the phenomenon of this lodestone or magnetite and why it is always a magnet. Now, again, the nail on the right is only a magnet because it's wrapped by a current carrying wire. And as long as current flows through that wire, it polarizes the iron in the nail, and the nail is magnetic only while the current flows. Okay, so ferromagnetism is this property of certain materials where they interact favorably with a magnetic when they're interacted with magnets, and they can become magnets. So a ferromagnet is a material which can be magnetized. Now, again, as I mentioned, not all materials can be magnetized. A lot of materials can't. As a matter of fact, some materials seem to be anti-magnetic. If you try to place them in magnetic fields, they kind of don't want anything to do with them. They kind of make only repulsive interaction with magnetic fields. So where then does this ferromagnetism originate? Now, first of all, maybe before we go any further, I should mention the origin of this word, ferromagnetism. The first two syllables, ferro, of that word are an indication to the Latin reference of iron. In ancient Rome, iron was ferrum. And even today in the periodic table, the symbol for iron is Fe, in reference to its use in ancient Rome for all kinds of things. And so ferromagnetism is the name given to materials which are easily induced to form magnets. And the reference is that it behaves like iron. Iron is magnetic. Not all iron can be made magnetic. Not all materials can be made magnetic. So if you are a material which can be made magnetic, the ferromagnetism means you are magnetic like iron, I guess, is what we would say. So ferromagnetism, it turns out, is a weird quantum mechanical thing. We'd have to get really deep into the idea of quantum mechanics to really explain what's going on. But electrons are charges. And I'm going to have a little picture showing you something about how that behavior leads directly to magnets in a moment. But so they're in amazing amounts of motion, as this cartoon is trying to represent, around the nucleus. So I'm kind of showing maybe a Rutherford-like picture of the atom. In the center is a massive nucleus, and then buzzing around it like satellites are electrons. Now, of course, these are electrons that are charged, and these are charges in motion. So charges in motion create magnets. So every atom has a little bit of magnetic character associated with it because it has charges moving in various motions. Typically, the motions all cancel. So as I said, you left to right, generating a north pole, but then if that same electron moved from right to left, it would generate a south pole. So what you can think of in electrically neutral atoms, almost invariably, now I will say again, almost invariably for most of them, their charges are all moving in so many directions such that they have so many equal magnitude north and south poles that they are net non-magnetic. Now, there's also another interesting phenomenon that leads to a charge in motion that can make it magnetic, other than just orbiting around the nucleus. So, of course, orbiting around the nucleus is a possible way to make a magnet, unless all those magnets are canceling. Another way in which electrons can make magnets is if they are doing what we call spinning. And I will show on the next slide an idea about what this thing we call spin means. And when atoms are spinning and have many of these electrons spinning in the same way, then they can be made permanently magnetic, and they can become materials like lodestone. So under the influence of a magnet, we can force materials to become magnetic, is the idea. Now, the main source of this in nature is that the Earth is a giant magnet. The planet we are riding on has natural magnetic character. And I'm going to say something about the origin of that in a moment. So there's a natural magnetic character to the Earth. And so deep in the core of the Earth, there have been rocks living near the center of the Earth's magnet for, well, the Earth is claimed to be 4 billion years. So for 4 billion years, this rock has been sitting in the Earth's magnet. Well, what has happened over 4 billion years is that the little internal magnets of that rock have gotten so lined up, so used to being aligned with the Earth's magnetic field, that they are permanently aligned. So now, if in a volcanic eruption, these rocks are sent from the center of the Earth to the surface of the Earth, where the magnetic field of the Earth is not nearly as strong, but these rocks have been spending billions of years in the presence of that magnetic field, they can't shake it. So permanent magnetic rocks that we find in nature are permanently magnetic because they were near the core of the Earth, and the core of the Earth is where the center of the Earth's magnetic field is. Now, as you can imagine, the Earth's magnetic field falls off with distance from its origin. Its origin is in the center of the Earth, so the further you get out from the center of the Earth, the weaker and weaker the Earth's magnetic field gets. So if these rocks spent billions of years down by it, they got an overload, intense application of this field for so long that they can't get rid of it. And now again, as I said, if they're belched upwards during a volcanic process, they remain permanently magnetic when they strike the surface. So let's now say another word about this idea of the electron spin. It's a little bit weird, but it's a little bit cool as well. So electrons have what we call spin. And here's what we can think of the origin of the spin. let's take an analogy from the Earth. We know that the Earth, if I put the sun in the middle, the Earth goes around the sun and gets back to the same spot every 365.25 days. It takes the Earth 365 and a quarter days to go from where it starts and return to that same point. So a year is based on the time that it takes the Earth to complete one orbit of the sun. Now, of course, typically we say that a year is 365 days. It actually takes the Earth 365 and a quarter days to exactly get back to the same spot. So what this means is, of course, and I think you can make the connection, every 4 years, we got an extra day. So that's why every fourth year, we call it a leap year. And every fourth year, we add a day to February in order to keep the calendar the same. So every 365 and a quarter days, the Earth orbits the sun exactly once. While the Earth is orbiting the sun, it's also spinning. This is what gives us our day and night. If the Earth wasn't spinning, one side of the Earth would be in permanent daylight. One side of the Earth would be in permanent nighttime. As a matter of fact, the moon, only one side of the moon faces the Earth at all times. Only one side. And literally, they did not know what was on the other side of the moon for centuries. Literally, they did not know what was on the other side of the moon until they could launch satellites up to the moon and take pictures of the backside of the moon. And people make, there were all kinds of fantasy stories or science fiction tales about what was going on the dark side of the moon, because we had never seen what was on that side of the planet, because there's no spin as it goes around the Earth. The Earth, however, spins as it goes around the sun. And I think we know how long it takes to spin. It takes 24 hours for the Earth to complete one rotation on its own axis. So every 365 and a quarter days, the Earth orbits the sun once. Every 24 hours, the Earth turns around on its own axis once. So we can call the 365.25 days the orbit of the Earth. We can call the 24-hour thing the spin of the Earth. So it spins as it orbits. So what I'm going to claim is that electrons do the same thing as they go around the nucleus. As they move around, they orbit. But internally, they turn on their own axis, so they spin. Both of these effects can lead to magnetic character. You can have an orbit magnet because you have charge in motion doing that. You can have a spin magnet and have a charge in motion as it moves around like that. Generally, the orbit magnets cancel. Atoms are constructed with all orbiting magnets canceling. The spin magnets mostly cancel, but in some elements, the spin magnets don't cancel. In elements where the spin magnets don't cancel, they can have magnetic character. So you can get magnetic character when these phenomena occur. So these are my little cartoons trying to show that. I can have an electron spinning, we'll say, and this is quantum mechanically maybe not exactly right, but it's good for a mental picture. If I spin my electron clockwise, then I will say that it generates a magnetic field with a north pole pointing in the downward direction. If I spin my electron counterclockwise, then it will, by spinning in the opposite direction, literally generate the opposite kind of magnetic effect. So these are the two characteristic so-called spins of electrons. They either spin to generate a north pole facing down, we call that a spin down electron, or they spin in the opposite sense to generate a magnet with the north pole pointing up, we call that a spin up electron. Now, in the periodic table, some elements have all canceling orbit spins and all canceling spins. Said that wrong. All in many elements, they have all canceling orbit magnets. That was the word I wanted to use, and all canceling spin magnets. They have as many counterclockwise movers as clockwise movers. Those elements have no magnetic behavior. But in many other elements, they do have canceling orbit magnets, but non-canceling spin magnets. So these are the kind that can now interact very strongly in a magnetic field. Now, if I take a look at this periodic, I thought I showed the table. I guess it's on the next slide. So there's essentially three things that can happen based on the way your electrons are spinning around your nucleus. If they are spinning in such a way that an incoming field interacts with them so that they are repelled by the incoming field, we call them diamagnetic. So diamagnetic elements have repulsive interaction with a magnetic field. Now it's funny, they know how to be repulsively interacting whether you bring a north pole or a south pole to them. If you bring a north pole to a diamagnetic material, it's going to push in the opposite direction. So it makes internally a north pole on it. If you bring a south pole of a magnet to a diamagnet, it's still repelled. So now it makes everything move the opposite way and makes a south pole internally, and it's still repelled. So diamagnetic materials are always repelled in magnetic fields because they're always generating the opposite the same magnetic field as the incoming magnetic field. Now, if you are paramagnetic, these are elements that are always attracted to a magnetic field, whether or not you bring north or south. So what you should then think, if you bring a north pole towards a paramagnetic element, it's going to make internally a south pole and be pulled to it. If you bring a south pole to a paramagnetic material, it's going to internally make a north pole, and opposite poles are attracted to one another, and so it will be attracted to that object. So this works whether you bring a north or a south in both the diamagnetic or the paramagnetic case. Now, the interesting elements that are known as ferromagnetic are ones that can be made permanently into magnets. Even when you remove, so the diamagnetic effect and paramagnetic effect are temporary effects, only working when the magnet is on. Once you turn the magnet off, they go back to what they were before. But elements that are ferromagnetic have the ability under the right conditions, that you can permanently magnetize them. Their magnetic fields will never go away, even when you turn the magnetic field off. Okay, so this table is trying to show the elements and their relative behaviors with regard to this. Now, let's be clear. Even if I asked you what one of these was, I wouldn't expect anything less than you to go look them up. Okay, so you could look up which ones are which in this table because the boxes are all color-coded. If you're in a white box in the periodic table and you see there's a smattering of them, not all, but there's a smattering of elements in the white boxes, those are not, they don't care one way or another. They could care less. You put magnets around them, they have nothing to do with the magnets. Then there's a bunch of yellow ones. Those are the diamagnetic elements. And the diamagnetic elements, as we said above, always make repulsion, always. So they're always pushed away by magnetic fields. Now, then the purple boxes are, I'm sorry. Oh, yeah, the yellow boxes are diamagnetic, the purple boxes paramagnetic. The red boxes are what we are calling ferromagnetics. Now notice there's not very many of them. There's two hiding at the bottom of the table, one behind my stop sharing sign, and there's three in the first long row of the table, including iron. So iron, cobalt, and nickel can be permanently magnetized, and also a couple elements at the bottom. So only 5 elements can be permanently magnetized. Now that does not mean that we can't generate magnets in other ways. We have learned very cleverly how to make polymers that contain materials that can be made into magnets. And what does that mean? You don't have to have all metal things sticking on your fridge. We got these little plastic things, right? We can stick the little plastic magnets that look kind of like pieces of paper, really, or not paper, but they really do look like pieces of plastic, but they've been magnetized. So material scientists have gotten very clever with what they can do to make magnets occur. But the elements themselves, if you want to make magnetic elements, you can see that permanently magnetic elements are very few and far between. And the most common, the ones at the bottom of the table, are very rare elements, not very common in nature at all. So the cobalt, nickel, and iron are, without question, go-to metallic permanent magnets. Now, in case you've forgotten, we showed slides earlier that noted that iron is the 3rd most abundant element in the Earth's crust. The first most abundant was oxygen. The second was silicon. Iron is the 3rd most abundant thing on this planet. So we've got a lot of iron around, and iron far and away is the material of choice to make permanent magnets, far and away. Okay, so now let's describe the idea of the magnetic field. And I'm going to show some pictures with arrows, just like we did with electric fields, to show which direction and orientation of push or pull you can get from a magnet. So just like with electric and gravity fields, magnetic field strengths fall off with distance. So magnets can provide, just like electricity or gravity, action at a distance. Again, if I want to exert force on this clock, I can only do it by touching the clock. I cannot push or pull this without touching it. The Earth's gravity field, I don't want to let my clock go, but if I let it go, the Earth can pull this clock without even touching it. And of course, that's the field of gravity. So magnetic fields and electric fields act the same, but instead of acting on mass, they act on, for electric, plus and minus, for magnetic, north and south. So the further you get away from a magnet, the weaker the field, of course, and these fields are conservative. And what that means is if you move around in the field in a closed path, you go cyclic around in it, you have to input energy. Here's what I mean. Okay, if I lift this up in the gravity field, I have to put work in. But I can let the gravity field do the same amount of work to drop this object back down. So if I want to move an object upward in the gravity field, I do work. If the object falls in the gravity field does work. And the amount of work I do to put in here is the amount of work you can harvest out of the gravity field. That's what we mean by conservative. So if I try to push 2 north poles together, I have to do work and exert energy. I am storing energy in the magnetic field. And if I let those north poles go, they will push apart with the same amount of energy that I supplied to get them close to each other. So that's what we mean when we say energy is conserved. whatever I put in is stored. And now you can get back out. So I can store energy in the gravity field and let the gravity field give it back to me later. I can store energy in an electric field by pushing a positive charge near another positive charge. And then if I want to get that energy out of it, I can let it fly back. It'll give me the energy back. I can store energy in a magnetic field by putting a north near a north. I have to exert energy to do that. But now I can get that energy back later by letting the magnetic field give it to me by pushing that object back to me. Okay, so that's what we mean by conserving energy. I put it in, I can store it, I can get it back out later. So the relationship between potential energy, we're not doing anything with formulas, so I don't care about that. So this is showing me about the relationship between how much energy I'm doing to push or pull it myself compared to how much I can get from pushing or pulling it out of that field. We're not doing any numbers in any equations. We don't need to even see that equation on the bottom of the slide. But what I do want you to be able to recognize is the direction of the field lines that come out of magnets, and it's got a definition similar but not exactly the same as we did for charges. Remember what we said. If you put a positive charge in the middle, the field lines come out from the positive. You put a negative charge in the middle, the electric field lines go in towards the negative. Out from the positive, in towards the negative. So the same idea is going to apply in magnets, but now if you have a north pole, it pushes another north pole away. So magnetic field lines go out from a north. Magnetic field lines come in or are pulled towards a south. So again, the analogy would be for charge. Positive charges push out field lines. Negative charges pull inward field lines. So the north direction of action is much like the positive direction of action for charge. The south magnetic direction of action is much like the negative direction of action of a field for charge. Now, if you look at magnets and look at their fields, these are the kind of things you would see. This is what we call a bar magnet. A bar magnet is a flat piece of steel, or could be steel, because steel is mostly iron, that has been permanently magnetized. So this is ferromagnetic, because it's probably iron. And one end of it is north, as we've indicated there. One end of it is south, as we have indicated there. And the field lines come out of the north, or the red end. And then if the other end wasn't there, they would just come straight out of it. Now remember, we did something like this similarly with charge. When I put a positive charge by itself, the lines just went straight out. But if I put a positive charge by a negative charge, the field lines off the positive were drawn to the negative. The same thing is what we are seeing here on a magnet. All magnets are dipoles. So all magnets have both ends of this behavior, a push and a pull. So if the other end wasn't there, the lines would just be coming just like they did for charges, radially out like spokes on a wheel, straight out. But because the other end is there, and the other end is an opposite field, it's going to pull the magnet lines towards each other, from the north to the south, and the field lines will bend around like this. Okay, now if you put two magnets near each other, notice when I put the opposite poles, it intensifies their connection between them. Notice the lines are all coming off the red one because it's the north. The lines are all going into the blue one because it's the south. But because the north and the south, unlike on the left picture, I've now got the north and the south really close to each other. That makes the field lines more intense or more dense. There's a whole bunch more closely spaced lines between the north and the south, and that's some kind of indication of the strength of the field. The field's going to be really strong when you get the poles really close to one another. It's really weak in the left picture, indicated by the spacing between the lines, because the poles are relatively far apart. Now, the middle picture is showing what happens when you put opposite poles near each other. When you put like poles near each other, and these are two north poles near each other, lines emanate outward from them. And again, if the other one wasn't present, they would just come off it like spokes of a wheel. But now the pole on the right affects the shape of the line for the left and vice versa. And so you get this weird kind of a picture for the way the field behaves. And you'll notice between the poles is a dead spot. There's no field because the fields are canceling. The vector action from the right is opposite to the vector action from the left. And so those vector lines in that region are just making one another go away. Now then, if you were to bend the poles around, or this is what you'll notice if I put two south poles together, I also will get a dead spot in the middle. And the only difference really between the right-hand top picture and the bottom left picture is the direction of the field. They're coming outward from the north and inward to the south, but that's really the only difference. If you make a horseshoe magnet, and I'm sure we've all seen the horseshoe magnet, this is exactly like the one in the top left, except the piece of metal is bent over. Why do we make horseshoe magnets? Because just like the top middle is showing, when you get the poles closer together, you're intensifying the field. So by taking the top left magnet, bending it into a horseshoe shape, you're getting its north pole near its south pole. Then between the poles, you're intensifying the magnetic fields. They're adding together. The vector part is going out from the north, but it's coming into the south. So those combinations allow vector lines to sum together to make stronger vector fields between the two poles bent in this fashion. So a lot of times you see horseshoe magnets, and the reason we use horseshoe magnets is in an attempt to intensify a magnetic field between the poles by simply getting the poles closer to one another. All right, now let's tell the interesting story of the Earth. The Earth is a huge magnet, and other planets in our solar system, such as Mars. Mars is our big goal these days. We're trying to get to Mars. Mars has no magnetic field, but Earth does have magnetic field. So let's contrast the differences between Mars and the Earth and try to describe what's going on to explain why we have one and they don't. Well, if you look and slice the Earth open like I've done here, you'll see that the geologists have divided the layers of the Earth up into different strata or named sections. So we have the so-called crust of the Earth, then we have some inner core, then we have some way down in there. We get further and further in. They have different designations of the names of the sections of the Earth. I don't so much care about that, but what I will point out to you is the deeper and deeper you get in there, at first it seems like it's getting cooler and cooler as you go into the Earth, like in a cave. But as you get closer and closer to the center of the Earth, you will quickly find it's getting rapidly hotter and hotter. And this is literally left over from the formation of our solar system. In the cataclysmic explosion of energy that formed all that is around us, the Earth was a liquid in a molten liquid state at one point, and over the 4 billion years of the existence of Earth, it has cooled. And as it has cooled, this molten, super super hot liquid material has solidified. So the outer layers of the Earth are kind of like one of those cherry-filled chocolate things that when you bite into, you got the harder crust on the outside, and then you got the gooey middle. Well, there's a gooey middle to the Earth. And the gooey middle to the Earth is still an incredibly hot region where there's molten material. Now, it is nowhere near the temperature of the sun, because the temperature of the sun in the center of it is crazy hot, because you're fusing. There's so much push in the center of the sun that atoms are getting squeezed together. So there's not enough pull in the center of the Earth to squeeze the atoms together that constitute the center of the Earth, but yet it remains incredibly hot from the origin of the formation of our solar system. Now, what is then in there is material that's moving. This liquid core of the Earth is in motion. And it turns out what the liquid core in the center of the Earth is what the majority of the Earth's crust is, other than the silicon and the oxygen. It's the iron. So there's all kinds of iron in the center of the Earth in a molten state that has been so hot that electrons are stripped loose from it. So there's rivers of charged iron flowing in the center of the Earth. This charged iron is charge in motion. Charge in motion creates a magnet. So the flowing river of iron in the middle of the Earth makes moving charge, and the moving charge makes magnet. As you go away from the molten center, the magnetic field falls off that it's being generated, but it's still sufficient to reach well into space. There's a significant magnetic field from the Earth that not only makes it from the molten part out to the mantle of the Earth, but not only to the surface of the Earth, but into space above the atmosphere of Earth. So moving charge in the middle of Earth creates this river of current. The river of current makes the magnet. Now, as we said, the direction of flow of the charge decides what kind of pole it is and where the pole is. So there's going to be a direction of flow generating a north pole in a certain region of the planet and a south pole in another region of the planet. Now, over the eons of existence of Earth, we can tell by looking at geological rock strata that the Earth's magnetic field has varied incredibly over the 4 billion years that the Earth has been around. Now, again, how do they tell this? They dig into a sample of rocks, and they can date how old those rocks are. Then they look for iron in the rock and look how it's lined up. And the iron in the rock lines up along the direction of the Earth's magnetic field. So in different rock layers of different age, they see that the iron in that rock is lined up differently. So that leads them to believe that the magnetic field of the Earth has been lined up differently many times. That also has proven that there have been long periods of time where there is no magnetic field in the Earth. So it's kind of like as if the flow of charge in the center has a certain direction. That puts the North Pole in a certain location. When the flow of charge in the Earth shifts, the North Pole moves. Now, we have known for a long time that the North Pole moves. First of all, the North Pole does not come directly out of the top of the Earth. It comes out of the Earth somewhere in Upper Canada, in the Arctic Circle, but not right at the top. We also know that the exact North Pole of the Earth has shifted with time because the British kept very particular records of its exact location for centuries. Why did they keep very particular location of it for centuries? Because it was incredibly important to circumnavigate the globe. If you wanted to be able to get in a ship and sail it on during the daytime or when it's so cloudy that you can't see the stars, then to map your position, you needed to use magnetic or compass information. Now, if there's stars up there and you knew the positions of the constellations at all times, then you could tell where you are by the location of the constellation. That's the number one go-to way. But if you can't do that, you can maybe tell from the sun's location. But if it's a cloudy day, you can't do any of those things. And if you want to know where you are on a cloudy day, you are stuck with using a compass, or a stormy day. You're stuck with using a compass. So the British kept very careful record of the exact location of the North Pole so that they could now use their compass to coordinate their compass from it to get location of a ship on the ocean. And it was noted even for the few hundred years that the British did this, that the exact position of the so-called North Pole was shifting quite dramatically. You know, a couple mile shift here and there even. So what that's an indication of is that this charge flowing in the center of the earth is mobile. And the current shifts in the center of the earth. Shifts so dramatically that over the eons of time that the earth's been around, the magnetic field has shut off sometimes. It has literally shifted sometimes, so that the bottom of the earth was where the North Pole was, the side of the earth was where the North Pole is, and all sorts of other interesting things have happened throughout time. Okay, so geologist records obtained from ferromagnetic rock layers show this has moved all kinds of places and has been all kinds of strengths. Okay, now, this is a picture showing the magnetic field lines coming out of the earth. And this should, first of all, this should be something very interesting that you note from what I'm showing in this picture. This shows how the earth behaves as a magnet. But look at what we see in the Arctic and look at what we see in the Antarctic. In the Arctic, I see one end of the magnet that is indicated as S. In the Antarctic, I see another end of the magnet that is indicated by N. Wait a minute. What is that saying? That is saying not what I've learned my whole life. This is saying the exact opposite of what I've learned my whole life. The North Pole of the Earth is the South Pole. The South Pole of the Earth is a North Magnetic Pole. Now that makes sense when you understand what a compass is doing. If you're going to be attracted to the North Pole, what attracts you to the North Pole? A South Pole. So in actuality, the compass reading of north is when you're interacting favorably. So the Earth's North Pole magnetically is the South Pole. Now here's where this is all messed up. For all these years, I've been sending Santa Claus letters. And I've been sending Santa Claus letters to the North Pole every year. And you know what? Santa Claus don't live at the North Pole. Apparently, Santa Claus lives at the South Pole, apparently. So this is messing with my head here. Now, what's going on? Again, the idea is we have defined North Pole as what points north on the Earth. What points north on the Earth is what is attracted to the north on the Earth. So technically, the North Pole of the Earth magnetically is a south magnetic pole to attract that north to it. That is out there. Okay, so during the incredibly crazy things that go on in the sun, here's basically what happens in the sun. The sun is a big ball of hydrogen. And there's so many hydrogens up there that they get attracted to one another. Now there are literally so many of them so close together that gravity does begin to work. Gravity pulls the hydrogen in closer and closer and closer. And the ones in the middle get so close to each other, they squeeze together. And the hydrogen in the center of the sun is pushed into each other so hard that they fuse and make helium. So in the center of the sun, hydrogen is being squeezed into helium. And it turns out it releases gazundous amount of energy along with that. So a gazundous amount of energy is released with the fusion of hydrogen into helium in the sun. But not only that, there's all kinds of energetics going on outside of that. Hydrogens are adding into heliums and making lithiums. And lithiums are combining into each other and making carbons. And so all the elements are being made. And our sun doesn't make all the elements. As a matter of fact, most stars can only make up to iron. So we're making elements in the suns by building hydrogens together, but releasing all kinds of energy, all kinds of light, all kinds of heat, and all kinds of charged particles. So from the sun, there is a constant stream of highly charged material bombarding the Earth. Now, because the Earth has this natural magnetic field, it pushes the charged particles that come from the sun away. The charged particles which come from the sun are known as the solar wind. The solar wind is this incredibly energetic, incredibly charged stuff that literally gets spewed out of the sun during the course of fusing hydrogen into helium. And it would be bombarding our planet regularly, and the detriment to life that it could cause could be irreparable. I mean, really, that could have stopped the formation of life on Earth, all this ionized, charged matter bombing us. But because of the Earth's magnetic field, it pushes the charge like an umbrella of the wind of charged matter that should be coming from the sun and striking the Earth gets pushed away by the Earth's magnetic field. Now, Mars, I said earlier, has no magnetic field. Why doesn't Mars have a magnetic field? Because it does not have a liquid molten core. It has iron in it, yes, but it is cooled iron and it is solid all the way through. So Mars is solid all the way through. There's no molten iron that can be charged. There's no molten iron that can flow. So there's no naturally being made, there's no natural magnets being made in the center of Mars. So Mars has no magnetic field. Now, fortunately, Mars is 90 million miles away from the Earth, farther away from the sun. So the solar wind has died down a lot there, but still there's going to be problems for humans on Mars because of all the ionizing radiation that strikes the surface of Mars due to the fact that it doesn't have a magnetic field to push it away from Mars like we have a magnetic field to push all this ionizing energy, high energy particles away that come from the sun. Okay, sorry, time is up. I hope, maybe if you weren't tuning in a little earlier, I had some issue with my Moodle stuff. Hopefully my Moodle stuff is being straightened out as we speak by the people who are looking into the backup tape of what happened to my Moodle. And then it's going to happen eventually. So until next time, peace out. Stop sharing.